Understanding how a computer really works. At first glance, this looks complex. Many of us were told to just memorize it. But behind this diagram is a simple, elegant story of how information flows. Let's trace that story together, step by step, and understand how computers actually execute programs. First, meet the system's workforce, the registers. These are small, high-speed storage locations, each with a specific job. These include the address register, program counter, data register, accumulator, temporary register, and instruction register. Think of them as specialized workers, each with their own role. All components communicate through a single shared pathway, the common bus. This is a 16-bit bus, meaning it can carry 16 bits of data at a time. Why 16? Because the memory is designed to store data in 16-bit chunks. The bus must be wide enough to carry the largest piece of data from memory in one trip. Next, the library, the memory unit. This system has a capacity of 4096 times 16. That means 4096 unique slots, each storing a 16-bit value, either data or an instruction. To access any of these 4096 slots, we need a 12-bit address, since 2 to the power of 12 equals 4096. This is where everything lives. Two registers don't place data onto the bus. They're the bridge to the outside world. INPR receives data from input devices like keyboards and passes it to the accumulator. OUTR receives final data from the bus and sends it to output devices like printers or monitors. They're our connection to reality. Now the engine room, the adder and accumulator. The adder and logic unit is the heart of the ALU. It performs the actual calculations. It takes inputs, typically from the data register and the accumulator. The result is stored back in the accumulator. There's also an E flip-flop used to store any extra bit, like a carry from an addition. This is where math happens. Nothing happens by itself. A central control unit uses signals to direct the traffic. Select lines, S2, S1, S0. These 3 bits choose which of the 7 components gets to place its data onto the bus. For example, binary 111 selects memory. Load signals tell a register to read the data currently on the bus. Read-write signals tell memory whether to prepare data for reading or accept data for writing. Every action is coordinated. Let's see it in action. We're going to compute A plus B times C plus D. To see how the system works, we'll trace the execution of a program to solve this expression. This architecture uses single address instructions, meaning each instruction works with one memory location at a time. Here's our program. Step 1. Where is the next instruction? The program counter holds the address 0 by 100. It puts this address onto the bus. The address register loads this address. Now AR knows where to look for the next instruction. This is called the fetch cycle, getting ready to read an instruction from memory. Step 2. Read the instruction from memory. The AR tells memory which address to look at. Memory is selected using binary 111 on the select lines, and it places the data from address 0 by 100 onto the bus. That data is the instruction load A. The instruction register captures it. Now we know what to do. Now the execution begins. Step 1 of our program. Load A, then ADDB. The system loads the value from memory location A into the accumulator, then adds the value from location B. The adder takes both inputs and outputs A plus B. The accumulator now holds this sum. First calculation done. Step 4. Store T. Save the intermediate result. We can't lose A plus B because we still need it later. The content of the accumulator is placed onto the bus using select signal 4 and loaded into the temporary register. TR now safely holds A plus B while we work on the next part. Step 5. Load C, then ADDD. The system repeats the process. Memory delivers the value from location C, loads it into the accumulator. Then memory delivers D. The adder adds them. The accumulator now holds C plus D. We've completed the second part of the calculation. Final step. MULT. The final calculation. The accumulator holds C plus D. The temporary register still holds A plus B. The adder performs multiplication. A plus B times C plus D. The accumulator holds the final answer. From here, it could be sent to the output register and displayed on your screen. The program is complete. From blueprint to a living machine. What was once a complex diagram is now a predictable flow. By coordinating a few key components with simple control signals, the computer executes complex tasks. The story isn't about memorizing parts, it's about understanding the flow. This is the foundation of how all computers work. If this made sense, hit subscribe. Thanks for watching.